Hello, everyone. I'm so sorry that in today's class, I forgot to record today's session. So now I just try to make up another video to cover today's course content. So first, let's review what we studied. So in the last class, we have studied that in the reinforcement learning, what we can see is only a series of states and rewards. But we don't know the transition probabilities and also the rewards function. But still, we want to calculate the optimal discounted future rewards. Then we have studied several algorithms such as supervised learning and online supervised learning. But our focus is on the certainty equivalent learning. So this is a model-based learning because it tries to learn all the parameters involved in a Markov system, such as the transition probabilities and the rewards function. Remember that we still have a sequence of states and rewards. Then if we see the state transition from S1 to S2, then we will draw a state transition like this. The probability is 1. Now we go from S2 to S3, and we draw another state transition. Probability is 3, is still 1. Then we go from S3 to S2, back to S2, so still the probability is 1. Now from S2, we go to S4 instead this time. Then we need to change the probability from S2 because all the probabilities should be added up to 1. Then this is 1 over 2, this is 1 over 2. Then now we have state transitions from S4 to S5, then we do the same. So basically in certainty equivalent learning, we try to learn the state transition probabilities. So these are data structures. We can count the number of times state is visited, and we can calculate the sum of rewards from that specific state, and we also count the number of times that the state transition from I to J happens. So in that case, we can calculate the rewards and the transition probabilities at any time. And with all this information, we can use the Bellman's equation to calculate the expected discounted future rewards. That is the reward plus the gamma, which is the learning discount rate, discount factor, and this is the probability of the state transition from Si to Sj, and times the expected future rewards of Sj. So this is C learning for Markov system. But C learning is too expensive. It can be as high as big O of NQ. Then we also studied the model-free learning. So it doesn't try to estimate the parameters of Markov system. Instead, it just maintains an array of the future reward discounts. Then the formula is this. So that is 1 minus alpha. Alpha is the learning rate times the discounted future rewards, and plus alpha times, this is the reward plus gamma times the future rewards in terms of Sj. So the reason that we use alpha is that we should put alpha close to 1 in the beginning. It means that if alpha is close to 1, then this term is almost 0. Because in the beginning, we are not very confident about the estimation of Si, the long-term discounted rewards for Si. But as time goes on, we become more and more confident in this term. But this term, as alpha is close to 0, so this term is becoming less and less important. So this is the idea. We should make alpha decreases as the time goes on. Then in last class, we also discussed the focus of the Markov decision process. The state transition is caused by an action. So for example, at state S1, if we use action A1, then it will cause the transition from S1 to S2. But still, we don't know the model of the environment, and we don't know the transition probabilities. We also don't know the reward associated with each state. Then the goal is the same. We still want to find an optimal policy. The idea is at a specific time, we want to know what is best action so that we can maximize our future rewards. Then formally, the reinforcement learning setting includes a set of states and a set of actions. So at each time, the agent observes a state ST and then chooses an action AT. Then it receives a reward RT and the state moves to ST plus 1. Then our goal is to find the optimal policy for the Markov decision process. So our solution to reinforcement learning includes model-based and model-free solutions. So for model-based, we still try to learn an explicit model of the transition probabilities and also rewards. And for model-free, we try to recover the optimal policy without ever estimating a model. So now let's take a look at the model-based methods. Remember the CE learning. In the CE learning, we maintain an array for count that counts the number of times state is visited. Then we also maintain an array for sum, that is the summation of the rewards received for each state. Then we also maintain a transition array, that is the number of times the state transition from I to J happens. So we can calculate the probability, transition probabilities, which is transition over count. Then we can use the Bellman's equation, so we can estimate the reward, and this is the discount factor. So we also have the probability distribution estimated and times the new state. That's the discounted reward for new state. We have studied that the model-based methods such as CE learning can help us just use value iteration to solve the problem. Now let's use an example. Suppose we start from S and we choose action of moving up. So we try to move up. Then we try this, several times. Then when we try to move up 10 times, for 10 times, I ended up at state S1. Then 2 times I ended up at the state S2. So what is the probability for? So what is the probability for, the state is S1, given the current state is S, and I use action of up. So the idea is it is 10 over 12 because we tried 12 times, then 10 out of 12 times we end up with state S2. And for state S1, and for state S2, then 2 out of 12 times we end up with state S2. So in this case, we can calculate the probability. So the best policy will be chosen by using this formula. So since we know the probability distribution, and we can estimate the possible future discount rewards, then the action that can maximize this term will be the action we should choose. That's the optimal action at the current time. So this method is called greedy solution. So we always choose action defined by the pi we have discovered so far. Then another method is called random. So it uses randomly pick an action to explore the world. So this one may not work very well, and it may take a long time before your algorithm can converge. So another method is called mixed. So that's a combination of greedy and random. So you have epsilon factor. So it's just greater or equal to 0, then less than or equal to 1. So you have 1 minus epsilon probability of choosing the best action defined by policy pi. And then you have the probability of epsilon of choosing randomly choosing another action. So in practice, the epsilon greedy approach may work even better. Okay, so next, let's continue our study for today's lecture, that is model-free algorithms. Remember that we can use model-based and model-free solution. So the model-free reinforcement learning, the idea is called Q-learning. So we define Q star, which is optimal solutions. The Q star SI A means the expected sum of discounted future rewards if I start in state SI. Then if I take action A, then I'm subsequently optimal. So it means that if currently I'm at state SI and I choose A, then what is the optimal discounted future rewards? That is defined by Q star. So then, since we have defined Q star, then we can define the optimal discounted future rewards. That is J star of S, right? So if I start from the current state S, and what is the expected future rewards defined in terms of Q star? So let's revisit the definition. So that is expected sum of discounted future rewards if I start in state SI, and if I take action A, and if I'm subsequently optimal. So at a specific state, I may choose different actions, right? Then if we use Q learning, then for each of the state action pair, as A1, I may end up a reward of -10. Then if I choose as A2, then I may have a reward which is 100. If I choose as A3, then I may have 1,000. So in that case, I should choose A3 to expand the current state, right? So this idea, we can define J star in terms of the action. We choose an action that can maximize the value of Q star of SA. So that is the action that maximizes the expected future rewards. Now here we are talking about the deterministic Markov state model. So it means that when you apply an action, it only generates one outcome. So that's deterministic. Then how can we define Q star? So basically it is equal to, since at the current state, I use action, I select action A, then I will receive a reward. So R is a reward function. So, at the current state, if I use action A, I will receive a reward defined by this action. defined by this function. Then gamma is discount factor, and J star is the optimal discounted future rewards. So this is the same as the definition, right? So at the current state, as I choose action A, and subsequently optimal. So this is optimal. Then we have already know that the J star is equal to this term. That is, we want to choose an action that can maximize the future rewards from Sj. So the state transition is from I to J by applying the action. So the idea is when we apply action A in state I, it will cause state transition to Sj, and also we will receive a reward denoted by the reward function, which is RSIA. So this is training rule. If we can list the formula in this way, then we can use value iteration idea to solve it. So here we are talking about deterministic reward. For example, at a specific state, if I choose go up, I will end up with state 2. So nothing else. So the outcome of an action is deterministic. And also the reward is also deterministic. It means that every time I go through a state, I will receive the same reward. Now let's take a look at the training algorithm. So what we need to maintain is a table for the Q values. So for each state action pair, we will have an entry in the table. Initially, we initialize all the values to be 0. Then at the current state S, I will choose as action A and run it, execute the action, and receive immediate reward. So here the reward is not associated with this state, but associated with the state transition. When I use action A in a state, then I will receive a reward. Then we observe new state as a result of the execution of the action A. Then we update the entry for Q estimate of SA as follows. So we receive a reward, and then we choose an action A prime that can maximize the future discount rewards starting from S prime. So action A leads causes the state transition from S to S prime. Then we assign S prime to S, then iterate through the algorithm again. So now let me show you an example to make it clear. So I assume this is state 1, state 2, state 3, 4, 5, and state G is the goal state. So goal state is also called absorbing state. So whenever you go into that state, you will never get out. So, and all the state transitions have a reverse of 0, except these two. So if you can directly move to the goal state, then you will receive a reward of 100. Then all other state transitions are 0. So now let's run the algorithm. So in the first step, we initialize the array to be 0. Okay, so now let's start from state 1. For state 1 is if I go up. If I go up, I will end up with state 2. Now let's just see, based on this one, the reward is 0, so we receive reward 0 and 0.9 times the max of the all these state action pairs with regarding to state 2. So now let's see state 2. State 2 has 2 entries, and both of them are 0, so this term is 0. This term is 0, then we will end up with 0. So if we choose go right, then we will enter state 4. So you see state 4 has 3 entries, but all of them are 0, so this term end up with 0. Then Now let's talk about state 2. So if we move down, it will go to state 1. You see all the state 1 Q values are 0, so this one is still 0. If we go right, we'll go to state 3, and state 3's Q values are all 0. Then we will end up with 0. Okay, so now let's talk about state 3. So for state 3, if we go left, we will end up with state 2. Then you know that the Q values for state 2 are all 0, so this one is 0. Then similarly, if we go down, we will go to state 4. Then we still have 0. Then if we go right, you see, if we go right, now we know that we will receive a reward of 100, right? And then for the state of G, if you go inside, you will never get out, and you don't have any further reward Q value. So this term is 0. So basically, if you go right, you will receive 100. Then for Q4, if we choose to go left, then we will end up with state 1, then we will receive the overall reward to be 0. So if we go up, then we will go to state 3. So state 3, all the values in the previous row. So remember that we only look at the previous row. So then it's still 0. If we go right, all the Q values in state 5 are 0. Then we still have 0. And for Q5, state 5, if we go left, we will end up at state 4. So we still 0. If we go up, you see, if we go up, first we will receive 100 reward, and the gamma times, and inside state, is 0. So basically we receive 100. Okay, so now let me clean these terms. Okay. All right. So now let's go one more round. So now let's talk about state 1. If we go up, we will end up with being at state 2. So state 2 are still 0. Still 0, then we will receive 0. So if we go right, we will end up with state 4. So state 4 are all 0s. We will the Q value is still 0. If we go down, then we will end up with state 1. Then state 1 are all 0s. This is 0. So if we go right, so we will go right, then the reward we will receive 0, right? Go right, then times sigma. So now let's see the maximum possible values in Q3. So you see, we have this one, and this one, and this one, right? So we have Q3 has 3 entries, and the maximum is 100. So basically, if we go right, we always, the Q value is going to be 90. So then if we go left, we will enter state 2. So we don't receive anything. If we go down, we will go to state 4. We don't receive anything. So if we go to right, now let's, this one is a little tricky. Let me still try give me more time to think about it. Okay, so for Q3, if we go right, we will receive 100, right? And plus gamma 0.9. And then what is G? If we go into G, then we only receive 0. So still this 100. Then for Q4, if we go left, it's still 0. We go up, that's, we will end up with state 3. So still, you see, this 3, then this one is going to be 90. Then if we go right, we will enter state 5. Then this is still 90. Then if we go left, in state 5, if we go left, we will enter state 4. Then all state 4 are 0. So then we have 0, then this one's still 100. Okay. If you want to go one more round, go for one more round, let's do it. So now let's talk about Q1, state 1. So if we go up, we will enter state 2. So now, state 2, the maximum value will be 90. So 0.9 times 90 is going to be 81. Then if we go right, we will enter state 4. So the maximum value for state 4 is 90. So then we will end up with 81. So if we go down, then from state 2, if we go down, then we will enter state 1. So, both entries are 0, so this is still 0. And if we go right, if we go right, the reward is 0. And we still use 0.9 times the maximum of Q3, which is 100. So still we receive 90. Now, if Q3, if we add a 3 and we go left, then we will enter 2. So you'll see 2, the maximum is 90. Then 0.9 times 90 is 81. And if we go down, we will enter Q4, still 90, so this is 81. If we go right, that's still 100. Now Q4, if we go left, we will enter 1, right? 1 is still 0. And if we go up, we're still 90. If we go right, it's 90. Then Q5, if we go left, we will enter Q4. So now Q4, the maximum value is 90. So 90.9, that is 81. Then this is 100. So this idea, right? With you can complete the table by filling out the rest 2 rows, but the idea is very clear now. So for Q1, which action you should choose? It doesn't matter, right? Because all the Q values are 81, you can choose either of them. So suppose, now let me use a different color. Now let me first remove all the okay. Then let me choose a different color. Let me choose blue. Okay. So, for example, let me just randomly choose this one, going right. Okay, then for Q2, which one we should choose? We should choose going right because it has bigger Q values. So for Q2, we go to right. And for Q3, which one we should choose? We should choose going right because Q value is 100. So we should choose going right. And for Q4, it doesn't matter, right? So we can go up or we can go right. So now let me just choose go right still. Then for Q5, 100 is bigger, so I choose go up. So you see, we have already identified an optimal solution. So that's optimal pi at state 1, we choose go out, go right. Then at state 2, we choose go right. But if you are at state 5, then you choose go up. So that's the idea. And this is one of the possible solutions. Remember that you can also choose this one, this action and here, because in both directions of the value of 81. So the optimal policy is not unique. So we have studied that Q star of SIA means the expected sum of discounted future rewards if I start in state SI and I take action A and I'm subsequently non-optimal. So we have already studied how to use Q star to represent J star. So that is, we choose action that maximize the expected sum of discounted future rewards. Then how to define optimal policy? That's going to be the same, right? So we choose action that maximizes the sum of the discounted future rewards. Then that action is the one we are going to choose, right? So just like in this table, for each state, we just choose one that can maximize the future rewards. So this is deterministic. This is deterministic world for the reinforcement learning. Then in the next class, we are going to study the non-deterministic worlds. But now you can start to implement your actual credit projects based on the knowledge we have learned in Q-learning. So on next Monday, let's try to finish the reinforcement learning, and then do some review in the week after Thanksgiving. Then probably we don't have a class on Wednesday after Thanksgiving. Then we will have the final demonstration of the actual credit projects on that Friday. Okay, so that's all I have. Thank you very much.